Hello everybody. Today we will be talking about the state space methods. Up to this point we've seen time domain methods for analysis and synthesis, and last lesson we've focused on frequency based methods where we had some body plots and we've tried to design and analyze systems using the body plot. And today we will be focusing on the state space models, because most of the time for some advanced applications it may be the case that you are using differential equations and you're modeling it. Maybe you want to design some state space based controllers. So we will be looking at this problem today. Now, as you might know, the state space representation can be converted into transfer functions, and transfer functions can also be converted into state space models. The only thing to note here is that if you have a state space model, there's only one transfer function that corresponds to the state space model. And we will see today how to calculate that basically. But if you have a transfer function model and you want to convert it into the state space model, well, there are an infinite amount of state space models that can represent your systems. You can view the state space model as a more detailed version, because transfer functions define only inputs and outputs, but in state space models you have internal states. So you're trying to, or most of the time you model the system with its internals. Therefore, there's only one input-output relation. So if you convert the state space to the transfer function object or model, then the reason that you have only one single possible way to do this is because there's only one relation between input and output. But since if you have a transfer function and you're converting that into a state space model, then the internals may change. With the same input-output relation, you may have infinite amount of different connections with the internal signals, and you can end up with the same input-output relation. So that's the reason why we have basically infinite amount of state space realizations. Now, of course, if you have a different model, then the connection and feedback structure here may change. So that will be updated today also in this topic. So before we start, let me just clarify that these state space models or methods are a little bit later developed than the PID controllers. So we kind of call them the classical methods, and this state space methods more like the modern methods. But don't think that this is the term modern shouldn't mislead you, since everything that was found here or every development that I'm going to talk about, at least because we're in the graduate level, undergraduate level, is not that advanced. It's not today's knowledge. This is known for a long time now. So, but what I try to say is that this is a little bit newer than the classical methods, and hopefully at the end you will understand why this has a little bit more developed features and advantages. Well, let's start with a given system. So let me remind you that the state space models are defined as x dot equals ax plus bu. So you have x dot, where x are the internal states, and that equals to ax plus bu. So you have basically a n amount of first order differential equations. So you can convert that into a nth order differential equation. Basically, that's the differential equation itself. Cx plus du will construct then the corresponding output that you're interested in. The relation between input and output are linear combinations of the internal states, and that's the reason why you can have infinite amount of internal states and connections, but from input to output you will have always the same relation. If you have such a state space model, then the stability or the sum of the known topics may be updated for this model. So we will see how to define these. We will see the comparison of controllers for both transfer functions and state space models, and then we will also see an observer, the Luenberger observer, the most simplest available observer you can find, and we will see what it is and why we need this basically. Okay, let's switch to MATLAB, and let's first of all define all our given matrices. So we have A, and basically this is 1.4142, and this is 2.8284. And then we have B, which is 2 and minus 1, and then C, which is 1 and 0, and then D equals 0. So most of the time for the applications that we will consider, there will be no D term. The same reason why we don't have that much biproper transfer functions, because this is the direct term. If you remember, this is Cx plus du, and if you just consider the part where y and du is, you can see that it relates the input to the output directly. So this is basically called the feed-forward connection, or the direct coupling here between the input and output. And the way the inputs are affecting the system states or internals is basically defined by this input matrix, and then we have the autonomous matrix that defines the differential equation actually, and C is the relation between the states and the output. So, and you can see that from here, because the input is x and the output is y, so this is a relation between x and y. So let me maybe remind you that x dot, so the derivative of x, somehow dx dt, it looks a little bit better, and bu. So we have a transition from input to a certain signal that we define, and this signal and the input are used to model the output. So we have u and y. So that's it. Now, our first task here today is to acquire the transfer function of the given state space realization and compare the step responses so that we are sure that this relates to, or this is exactly the same system or model. Now, since we need the transfer function, there are several ways to accomplish this, and one of them will be basically the control system toolbox again, and the other one will be the symbolic toolbox. So you can use both of them, or one of them will do the job, but we will see both of them for a reason. Since you know that we are focusing on the basics, the theoretical aspects here, we have to code it ourselves in order to improve our understanding about this. Now, you can just go ahead and define a system model here, let's say sys, as you would have done with the transfer function. The only difference, transfer function abbreviation is TF, and steady state state space is basically SS. So yeah, you have to give the A, B, C, and D matrices that are necessary to define the state space, but you can give num and then, since numerator and denominator are used to define the transfer function. So that's the reason why we will use this SS here. And if you type this in and run this, you will see that it immediately gives you the A, B, C, D matrices back. If you don't want to see anything as an output, you have to put in a semicolon, but otherwise you will get this here. And you can see the internals here. As far as I know, for documentation of SS, you can give states names. As far as I remember, I never use it very that often, but as far as I know, you can name these states, and there's a very well documented this is very well documented, and you have all the necessary there it is. I found it. All the necessary information is here. And you can give the state names, position, and velocity. The reason for this being handy is that most of the time you will use some Newton law or some physics to model your system. Then obviously you will have position or velocity as states, or it can be anything, but states will have a representation or meaning in the real world, so you can keep track of which signal was what, and the input is, for example, here a force, and then you can see that we have a force and we have an output, and this is the relation, basically. So you can read this documentation in order to use some advanced techniques, but it is also sufficient to just define your system. If you know what you're doing, it will be no problem. So we have the system. Now, how can we find the transfer function that's here? Well, basically, you can just go ahead and use TF and provide the system here as an object, and it will give you the transfer function here. So you can see that you just got the transfer function that corresponds to this. So TF can not only be used with numerator and denominator, it can also be provided a system object, since this SS is a system object, and we will see it here that the SS is basically a 1-by-1 SS. So if you provide it to TF, or if you pass it through the function TF, it will give you the transfer function. But this doesn't help us much, because this is only important when you know what you're doing. If you're a new learner, I recommend you the other way that I'm going to show you now. Now, let's get rid of this for a moment, and let's look at the transfer function calculation manually. Now, since x dot equals ax plus bu, this is our first equation basically, I need to be able to take the Laplace transform here, since at the end I want to end up with a fraction of s variables, of polynomials of s's, and the s is the Laplace variable. So I can use this differential equation, and I can just convert it into, or transform into the Laplace domain. So assuming that I have 0 initial conditions, this will give me s times x here. So let me show it with a capital S to distinguish the time domain and Laplace domain representations. So I will have ax plus bu. Now, if I work on this equation, I can see now that I can arrange my variables so that I can find a relation between x and u. Maybe x divided by u. The transfer function between u and x basically is since x should be left alone, I need to take the inverse. Since I'm using matrices, the order of the inverse may be important, is actually important. So let me just arrange this. So bu, and this will give me the identity matrix, and therefore this will vanish. But this is the inverse here. So this term will vanish, and I will get x divided by u as sx six, because this is a matrix, this is a scalar. In order to be able to take the difference, you have to have both matrices. So basically, what I get here is that my relation between the input and my defined internal states is Si minus A inverse times B. So I've just used the fact that this is a differential equation, and I can use the Laplace transform. What now? Well, I have another basically equation that is something like this. Now, if I divide every term by u, I will get the transfer function relation basically. Let's denote this as a capital Y. What I get will look like the following. This will be my equation because I've divided by u and I've taken the Laplace transform. Since there's nothing dynamic, this is a static equation, I can just get the capital representations, and this will be the Laplace version. Now, y divided by u is basically my transfer function, so I'm looking for that, and I need x divided by u. And interestingly enough, I've worked out the relation of x divided by u, or the transfer function between the states and the input. If I plug this in, I have the transfer function already defined. I have to multiply C with the Si minus A inverse and B, and I have to add D. Because D is the direct coupling, it also shows here that it is just standing on its own. And I'm adding the output, then there's the input, and then there's the internal. So input-output relation kind of makes sense that it looks like this. So I'm going to basically use this expression now. I can get rid of these here. The only thing that I need is to just define this as GS, is to change this into the MATLAB identity function. And I really don't know why MATLAB decided to use this interesting abbreviation or function name for identity, where it could have been identity as here, but I don't know. Maybe there is a reason that I'm not aware of. But I also sometimes use Mathematica, and there's we have this identity matrix, and it makes more sense. I don't know. Maybe it's only me. I don't know. Now, this will be basically the simplify the transfer function representation. Only the problem here is that I have defined it in the S domain. I mean symbolic toolbox. If you want to convert it, you will be able to convert, and you can see that it gave a different output. By the way, most of the time I experienced this. Using the symbolic toolbox may get rid of numerical errors, but if you use the control system toolbox, there may be some problems. So I don't know what the reason is, but sometimes this method works way better in terms of numerical errors than the MATLAB predefined function. Now, I can also convert this into the transfer function object by taking we've seen this most of the time, the num_dan function, so the numerator and denominator. Since I need the step responses of both, I need to convert this into num_dan, and then the num will be the double of coefficients of this num vector, and I need all the coefficients of S in order to be able to define the numerator and denominator and pass them to the transfer function. Now I should maybe update this so I have this, and then we will just use the TF. Since I have the coefficients and since they are double, I can provide this, and I can get this here, the continuous time transfer function. Now it will be possible to use step on this, and you can also use step on SS objects, since these both are system objects, you can use systems with step. So everything that you can do with the transfer function, if it makes sense, can be used with these objects, these state space realizations. So let's say that cis should be black, and we have GS, which should be, let's say, blue. And if I run this, we have a problem. Did I not define it right? I'm not sure. Let's check it. 1, 2, 2 minus 1, 1, 0, there is 0. What could be the error? Interesting. With A. Oh, okay. Makes sense actually, but I should give it a time constraint, then I will see where it is. There we go, basically. I didn't convert it back to that, okay. But this is still interesting. System. I guess I know what the reason is, but now this should be square root of 2 as far as I know. So I should maybe define it with square root and 2 times the square root of 2. What happens then? Still an error there. I don't know why this is the case. But it should be because of the numerical error that will be caused by the following. It's still not exactly the same, so this term shouldn't be there. So this is the reason why I'm most of the time using the other representation, since you can see that this is 1 and 2, this is 1 and 2 times the square root of 2, so there is a linear relation between the states. Actually, there are no 2 states. It seems like 2 states, but this is a first order system, and we will see that in a minute. And so this is a mathematical error, as I've told you. It should be the same, but MATLAB has some problems, and I can demonstrate to you that this does actually work, because this is a problematic system. If I provide a 1, 2, minus 3, minus 4, a better system that isn't deficient, basically, you will see that it immediately matches, and I can also plot one individual, maybe figure 1 and figure 2, and putting them side by side can show you that this is basically the same system, and this is working. The only problem here is with deficient systems, and the reason there is that you have to take an inverse. If this inverse isn't available, then there's a problem, and MATLAB experiences that problem. It might be the case if you have a deficient system that you get a problematic view. And this also shows you the importance of knowledge in terms of theoretical basis, because if you are not aware of the deficiency, if you don't see it, then you might ask yourself why this is the result, because this is basically an integrator with gain 2 and nothing else, but you get a fading response, which shouldn't be the case. Let's give it, let's say, 100 seconds. After 100 seconds it becomes unstable, but it's the reason why, because of numerical problems. Let's see if we can zoom in a little bit. Actually, it's not possible. I shouldn't even attempt that. Maybe 20 seconds will show me what's really happening. Well, basically it's not working because that's not the this is not the model that I have. And if you want to see why, let's see if we can convert it back. Let's get rid of this here. Now, I am not sure, but I should be able to path also the transfer function itself back to the state space realization, and it gives me immediately a first order system, which is basically an integrator with gain 2. Because if you use this, let's say this is sys2 here, and we've converted GS back to the state space. I'm sorry. And then let's say this is GS2, and then I'm converting it back. Now, interesting things will happen. Let's see. We have this, and then converting it back gives me this. So I did basically use this here. I've converted this back, and I have again calculated the transfer function. Basically this line works, but if I do something like this here, if I give A, B, C, D as a state space system and then find me the transfer function, it gives me this awkward transfer function. But if I say, okay, give me back the state space realization, it will mess up because there are infinite amount of relations. It will give me some other representation. So keeping track of this or seeing what the problem is just by using the control system toolbox may be a little bit painful, but the only thing that you can maybe look for is the rank of A. That should give you a hint, because this has a 1 rank. This is a 1 rank matrix, so it should be a full rank matrix, but it is not. If there's a relation, you can see that. But that's not the only problem that you can face, and we will see what the problem may be. Now, in short, it is a good idea to know what I should do in order to transform this into the transfer function. So basically, if you have A, B, C, D, you can define S, and then this here, C times Si minus A inverse times B plus D. If you have this step, I've done this step, then you will see that the numerator, denominator, all the coefficients, and then convert it to TF, and you will get the GS. That is the transfer function representation here. Now, how can I, and this is a little bit more tricky, how can I convert GS back to the state space realization or model? How can I acquire the state space model using a transfer function object? Now, the best thing here is to use a decomposition of the transfer function. Let's say we have a different system, and let's use the different system because this is efficient, so it will be a little problematic to show what's actually going on. Let's give it -3 and -4. Comment this out. So let's say we have GS as a transfer function. A transfer function like this is given. How can I find the state space realization? Well, basically, the first step would be to get rid of the numerator, and keep in mind that this is only my method. By my method, I mean I prefer to do this. You can do it differently, but since there are infinite amount of state space realizations. But I like to get rid of the numerator here, which means that I place a 1 here, and define this as the relation between the input and the states. So what I mean by this is it should be looking like this. 1 divided by, let's say, s squared plus 3 times s plus 2. So I get rid of the numerator. I will come back to the numerator, but the only thing that I'm using here is the denominator. Why do I do this? Well, basically I know that the internals are modeled with si minus a, and a is concerned with the stability of the system. So if I have a, I can determine the stability of the system. And the denominator of the system is also about the stability of the system. So basically, the main behavior and the stability of the system is determined by this denominator and a. So by getting rid of the zeros or the numerator of the transfer function, I'm only focusing on the characteristic polynomial part, which should correspond to the A matrix here. So if I have this, I can then multiply or maybe rearrange my my equations so that it looks like this. If you multiply with that and then that, you can see that you will get this here. So, and if you expand this, you will see that we have something like this here. Now this gives me a hint because this is s times x. This is the second derivative, dx square divided dt divided by dt square plus 3 times dx, since I assume for transfer functions that the initial condition is 0, dx divided by dt plus 2 times x is equal to u. Now at this point you have the differential equation back. What you can do now is to define your states and choose x as the first state, and then you look for the derivative of the state, dx1 dt. That gives you dx divided by dt. And you will name this as the new state. So then you will have dx2 divided by dt, and this should give you d square x divided by dt square, which means the second derivative of x, because it's the derivative of the derivative. And you will be able to use these in this equation or expression, and you will end up with a nice equation set. Now, first of all, I can see now that dx1 dt, which is important, is equal to x2. And then I can see that here we have basically d square x, which I've written wrong. Okay, d square x dt square is basically dx2 dt. So I can substitute dx2 into this here. So this will give me basically dx2 divided by dt. And then dx dt is basically x2. So I can plug in that. So x1 is x. So I have this equation here. So if I rearrange this, I will get what I actually want. So this will be minus, or I should even put it here, plus, and this is also minus. So maybe it's a better idea to sort the equations here, the states here. And what I did end up is I have this first equation and then this second equation. So left hand side we have dx, right hand side we have linear combinations of x1, x2 and u. So if I'm going to define the matrix version here, it gives me for the first row I have dx1 dt. It doesn't depend on x1, so x1 is 0. It depends on x2 and the coefficient is 1. And then for the second row where dx2 dt is calculated, I have minus 2 of x1 and minus 3 of x2. So this is basically my A matrix. After that, I can see that I have only input in the second row. So the first row doesn't have an input, and the coefficient of the input is 1. So basically, I have converted this into this. And you can also see that there is a relation. -2, -3 is here, and this is basically standard stuff, because you will every state that has a derivative up to degree n will be defined as a new variable. So that's the reason why we will have a template here, 0, 1. And then my input will be in the last equation, because all the n-1 rows are relations between the internal states. So the only state that will be used for the actual differential equation is the last state, the nth state. So now I have basically the relation between 1 divided by s squared plus 3s plus 2, or namely x and u. So the only thing left, and I've already shown you that I should find the output. So let me give you the Laplace equation, cx plus du. So I can basically divide by u, and I will see that this is cx divided by u plus d. Now this means that I have a, I have b, so the only thing that is left is 2s plus 6. And I don't even need this. I can see now that y should be equal to, let's say, c1 x1 plus c2 x2 plus du. Now, since this is 2s plus 6, I can say that this is 2sx, and this is 2sx plus 6x. So basically this was called x2, this is x1, so I have 6 of this and 2 of this, and there's no direct coupling term, so this is 1. So this is 0, I'm sorry. So there's no u term. So this shows me that d is equal to 0, and then I have c, which is 6 and 2. By the way, there is a certain symmetry or certain rule to this, because you can see that the numerator coefficients are reversed here, and then some of the denominator coefficients, namely all the coefficients except the highest order, are also reversed here. So that's that. If it's biproper, then you should basically look for a integer part of this, or a non-fraction part that will directly be the direct term, so d, so that, and then you will use that. So basically, by just looking at this, I have acquired the state space model here, and you can see now and define your system using this here. A and b, so b should be a column vector. So there we go. And you can pass it back to the transfer function object, and what you will get is the same, the point where you did start. So variations may be 6 divided by s squared plus 3s plus 2 can be the relation between the input and states, or you can use 2s plus 6 divided by the denominator as a relation between states and input, or you can do what I do, just get rid of this, and 1 divided by this gives you the relation. So there are infinitely amount of possibilities, because b times c should be fixed, and you can choose b and c accordingly. That will give you the infinite amount of solutions. Or you can also have unnecessary states, so you can also give a third order transfer function, a state space realization for a second order transfer function, and it will work. And this is basically the commented out system is such an example. Now I've shown you how to get back and forth, so basically it is a good idea to remember this here. Let's look at our PDF here. Now we have basically compared their results. Now the next question is to calculate the stability interval for a p-type controller and design a state feedback controller for the given state space representation. Well, basically, since you can acquire the transfer function, you are asked to find a stability interval, and then don't switch to the transfer function. Use this here and try to design a state feedback controller. I say try to because this is a deficient system. Not all systems are like this, but I have chosen this especially for the sole purpose of showing the advanced problems here instead of the usual conversion. Okay, now since I have GS, I can just use R locus, and even this R locus will be very simple because it's an integrator. So let's get rid of the graphics and let's call figure 1. Now this tells you that if you want to place your pole, let's say at -1, hope I can click it. There we go. You have to use half the gain. Basically that's what it tells, because you have a gain of 2 in the system embedded. Or I can show you basically that 2k divided by s is the feed forward, and the closed loop using this will be this divided by 2 times k divided by s plus 1. So if you multiply with s, this will be 2k, and then this will be 2k, and then this will be s. So the numerator is 2k, the denominator is s plus 2k. If you want to place a pole at 1, you need a gain of 0.5. Right, let's do that. Basically, the stability interval here, by the way, is 0 to infinity, and there's no negative controller gain that can stabilize the system, because it will be moving on the right hand side on the complex plane. So basically the stability interval is 0 infinity, and your controller can be designed by 1, if 1 is the pole, divided by 2 will give you the gain, and you can just get TS, which will be the feedback, and you will use K times GS comma 1, and you will have TS here. There we go. Now what about state feedback control? Now keep in mind that the p-type controller and the feedback structure is as usual, but the name state feedback actually suggests you that you are using the internal states, the internal defined signals, and you will use the linear combination of that for feedback. So this is a bit different than designing a p-type controller, because your p-type controller has an input that is the error. So we have an error r minus y, and we are feeding back that information to the system, and we apply that as an input. But here in this case, in the case of a state space feedback controller, then there we will use k1 times x1, k2 times x2, the sum of this, and we will feed this back. This is not the error feedback, this is the state feedback. So basically they are a bit different, and this may have some advantages or disadvantages, we will see. Now, how can I try to design a state feedback controller? Well, basically the Ackermann formula helps us. Let me just use the Ackermann formula here. You give it the system, and I will give it the state space system here, A, B, C, and D. Oh, I guess it wanted A and B, and then the poles. So let me give it -1 and -1, since it's a second order system, and let me hit run. So you get a singularity problem, and let me show you what the Ackermann formula basically gives you. It asks you A and B and the poles for the closed loop that are necessary or that will be used for assignment, and you have x dot equals ax b u, and it gives you u equals minus kx. So this is what what I was talking about. It's not a feedback of error. There is no error here because there's no reference here. There's only the states that are defined as internals, and I can, hopefully, I can feed them back with a linear combination of the states. I can construct an input and feed it back to the system. So this is much different than the other one as I've talked about. Now, there's also an error band here, so it might make some numerical computational errors. But the problem here is basically that I have singularity here. So the Ackermann formula itself is already known. So I might skip the, let's say this is Ks here. I might skip the whole Ackermann formula. I can try it myself. And the formula is as follows. So what this tells me is that we have a row vector of 0, 1, and this will change according to the degree of the plant. And then there's phi c, the inverse of that, which is basically the controllability matrix, and we will see what that is. And then we have PDA, which is basically the linear combination of the matrix A, but this linear combination comes from the characteristic polynomial or the desired polynomial, much like in the time domain and the method where we used PDS to design dominant pole assignment controllers. This is the PDA, this is the whole closed loop. The only difference is that this is of degree n, not of degree 2. So this is the whole closed loop denominator that we are aiming here. So what is the controllability matrix? The controllability matrix is b times a times b, comma a squared b, comma a cubed b, comma a to the power of 4b, dot dot dot, it goes on. Now I need the inverse of this matrix here, and then PDA, where PDA is actually, let's define PDS. Since I want to assign my poles at -1, this is basically the square of s plus 1, because there are two poles that coincide at -1. The polynomial that's describing this is PDS. And PDA is, by the way, since this is s square, I will take a square plus, I guess, 2s, so 2a. So you're substituting s with a, basically. And then there will be 1, so I will be adding the identity here. So the coefficients are coming from the coefficients of the desired polynomial. S squared plus 2s plus 1, so 1, 2, 1 are the coefficients, and I'm applying this to the matrix A, or I'm substituting f with a, depends on your view, how you view it. And we can then run this, and again we get the same error because this is the Ackermann formula and it's not possible to do this. So why are we not able to use this? Basically because the controllability matrix is singular. So if I have phi c, you can see that there is a 0 column here, and the first one is b, 2 minus 1, and a times b is exactly 0, 0. So this is a singular matrix, and you cannot take the inverse of this. Now, what should I do then? Basically, this means that you have controllability issues, and most probably your system is not degree n. Maybe it is n minus 1 because you have just one column and the other column is 0 column. So maybe it's a too high of a degree. So how can I accomplish this then? What should I do? I will show you one method that needs a little bit thought to it. And namely, I have GS. Maybe I can go ahead and say that this is my actual system. System 2 is basically the transformation of GS. If I do this, I will see now that sys2 has different A and B matrices, but I can also see that this is basically an integrator, since x dot equals 0x plus 2u. This means that x dot is equal to 2 times u. So this is an integrator with gain 2. Using this, I might update my A and B matrices. Since this is of order 1, I have to get rid of this square because the characteristic polynomial that I'm aiming should be with a degree n, where n is the degree of my system. Since I have a first order system, I should have a first order polynomial. This means that my PDA will also be different. This will be in fact my PDA because plugging s equals a gives me a plus 1, but 1 should be identity because a is a matrix in order to be able to take the sum. And then my phi c, which is also degree dependent, will be b now, and b was 2, so I will have 2. So obviously if this is not 0, I will be able to take the inverse. Now this will narrow down to 1. I will get rid of the zeros, and this should give me Ks, where Ks is the state feedback matrix here. I might have a slight problem here. Why do I have this? Oh, I'm using A where A is not that. This should be A because A is 0. You can see it from sys2. A is 0, and if I plug in A, it will give me only 1, which is basically identity 1, which is basically also 1. So this is 2, and I will hopefully get the state space state feedback controller, and this state feedback utilizes 0.5 as the feedback, which was the case of the p-type controller. Now you can see that if you have a scalar system, or namely a first order system, the p-type controller and the state feedback controller are the same. So if you have a first order system, then you're basically feeding back the output. But keep in mind that the Ackermann formula needs to have a minus because it told us that u is equal to kx. So there's also a minus sign. And keep in mind that this equivalence is based on 0 reference. So you should use 0 as the reference. Then your error becomes minus y, which is minus cx. So here we have k, and they will be the same. So basically, what I'm trying to tell here is that the p-type controller and the state feedback controller are the same in a sense for scalar systems. They are similar, what I mean by this. So let's look at a different method. I have used basically the control system toolbox that should help me out. But I want to basically use my second order model. Is it possible to get the same effect here? We'll see in a moment. A squared plus 2 times A plus identity 2. and then we will have b and a times b here, and then a 0, 1 vector, and then the inverse of this and PDA. Now, as you remember, the problem was that I couldn't take the inverse, but I might get the pseudo-inverse, and that can sometimes work, but I'm not sure why we didn't get the effect that we were looking for. Let me just try it with a different a here, -3 and -4. If I run this and use the inverse here, -1 and -1. So let's also look for the closed loop here. The closed loop is, by the way, a times b times a minus b times k, s here. And you can see that these poles are assigned as we want them to. Now, where does it come from? Well, basically, you have x dot equals ax plus bu, but u is minus kx, so minus kx is here, so they will be summed because they both depend on x. Now, you had the eigenvalues or the poles of a. Now you have the eigenvalues of a minus bk, so that's the reason why you are changing basically the closed loop behavior, since you are changing the eigenvalues of the differential equation or the system, and this is basically an injection. So here the P inverse should give me the same thing. If I have the other A, I'm not really sure why. Okay, there we go. We have something at least, but I guess this comes from the fact that my system was messing up because of the singularity. So now phi c is this. If I have P inverse phi, I get this here, which is basically a... Oh, I see now the problem here. This is 0, 1, so it takes the last row here. So that's the reason why it doesn't work. And I guess there's no way of solving this. Maybe some transpose action, I don't know. No, it will be not possible to do what we want, because the pseudo inverse sometimes gives the result, but in this case it doesn't work. Maybe let's change it to 2. It will always give me a ks vector that is 0. Yeah, so it's not possible. Maybe let's try one thing out, and if it's not working, then it is not. Oh, we have to change this here. Let me quick this should be 5 and this should be 6, I guess. And if we run it, nope, it's not working, because the P inverse phi c gives me such a vector that it's not possible to assign it. And this expression is here very crucial, and you can see it's not working. So the pseudo inverse or the Ackermann formula is not usable if you don't have full rank controllability, which means that the system should be totally controllable. If that's not the case, then unfortunately you will not be able to calculate it. You have to maybe reduce your model, since you have most probably you have unnecessary states defined. That's that. Now, if we change the system, by the way, this works. You can see that you don't even need pi inverse, and you can see that there is a vector to that, so you can use that with PDA. But if you have this, it works. I'm giving it 2 and 3, and at the end result I get -3 and -2, so I can assign it. But as I've told you, even though it seems like if you use P inverse, it should be the case, but it is not. You are not able to assign a poles. You have to reduce your system, and then you should go ahead and design your state feedback controller, because the feedback controller needs needs all the states in order to take the linear combination to construct your feedback. But if there's a controllability issue, then you cannot change the pole of you cannot. Looking at the rank, you can determine how many poles are movable and how many are not, but there is a problem with assigning all the poles. Now let's look at our task here. Now it says that design, calculate closed loop poles, acquire the state that we given above, design feedback control, design post pole calculation, see, compare the closed loop. But basically, I've covered everything by talking about this, but I will show you the formal definition here, so that we get a nice result here. Now, let me basically show you the solution here. Here is the formal conversion, and you can see basically what happens is that MATLAB calculates this value slightly on the bad part, because the approximation is not exact. So it thinks that this value and basically this and this are not canceling each other out, so you get this weird transfer function that's second order, but still there is some singularity issues. So basically this is an integrator, and if you apply step, it should have a slope of 2, and that's basically it. If you plot, by the way, the step response of the internals, you will get this. There are 2 ways or even 3 ways to accomplish this plot. You can go ahead and use Simulink, drag and drop the state space. I have a video on that. You can check my channel out, by the way. And if you want to code this, you can use an ODE. That's also possible, and that's also in the same video. You can use discretization and get a discrete model and use the for loop. That's also somewhere available in my channel. I guess it was about the control input restriction. So there should be a video with control input, so you can carry out the simulations. And you can also see that the output is more like x1, because you use x1 because the C matrix here was 1, 0, I guess. Not this one, but basically this one here. Because C was 1, 0, so this means that the output is directly related to x1 and not x2. 0, x2 is taken into account, so that's the reason why we have similarities here. Now the closed loop system using a p-type controller is 2k divided by s plus 2k, and the stability interval, as I've told you before, is this, and then you have this controllability, and you get this rank 1. This means that you have basically a first order system, because there are controllability issues here. So if you reduce it to the first order system, then you will get A0, B1, C2, and D0. Basically what I mean here is that you can change B to S2 and C as 1, or 4.5, so 4 times 0.5 gives me 2. You will always get the same system, because A has a certain value, but after all, this decides what the numerator will look like. And the only problem is that, or the only necessity here, is that B times C should be fixed at the same value, so you can generate as many as state space models as you want. Since this is only a scalar, this is 1, and you get S plus P, and plugging it into this gives you K equals P for this one here. And if you want to assign a pole, you use 0.5, the other one uses 1. It depends on the model you're using. If this has 2 in it, then this is the case. If it would be equal to 1 and this would be 2, then as you've seen, 0.5 will be needed. So basically that's that. For the new system, you have zeta 0.6, and then you have this p-type controller problem here that comes from the coefficient method or the algebraic method, and you get a controller, you assign these poles here. And then we are converting this into the state space realization. As I've told you, I always take the numerator as 1 and look for the x and u relation here. And then I work out the differential equation. Using this differential equation, it's always possible to get this structure, and you will always experience that the first row or the first n-1 rows will be a special structure that generates 0, 1, 0, 0, 0, 1, and then your differential equation coefficients, namely minus this and minus this in this order. And the only input here is here and not in the other ones, because they are showing us the relation between the states. And then considering 6s plus 12 later, based on this transfer function part here or the realization there, you just need this here, because you get 6s plus 12 times x, and this corresponds to this in the time domain. You will get the coefficients. Since this is x2, this will be here. Since this is x1, this will be here. So you will get the C matrix. Since there is no direct coupling term, you get the state space here. Now we will use the same poles to assign it. Remember that we have designed a p-type controller. We've shown that this is basically a pole pair of the closed loop. And then I'm basically trying to design the same state feedback controller here. We have PDA, we plug in A, we get this matrix here, and then we have the controllability matrix that looks like this. And then we use the Ackermann formula, and we get K equals this. Now, here we can clearly see the difference. The p-type controller is just one gain on its own. It is a 1 by 1 variable, but the state feedback controller is a 1 by n feedback matrix, basically, or vector, because you will need to assign every state a coefficient, and these coefficients will be multiplied with the states, and the sum will give you the control signal that you're looking for, and basically a minus sign is also needed. So then you can plug this in and you get this A minus BK. Now let's look at the poles here, and you can see that A minus BK gives you basically this matrix, and the eigenvalues are the poles that we were looking to assign here. Now we can also work out the transfer function in using the state space that we've acquired here, because this is the new resulting matrix, and this will be the same. You don't change anything here. The only change is in this A matrix here. And basically what you get is 6s plus 12 divided by this here. But if you would have used the p-type controller, then you can see that this gain is also here. So k times this comes here, and we have figure 3, which demonstrates the difference here. Now we can see that the p-type controller generates this output, whereas our state feedback generates this here, and there's only the only difference here is the gain in the closed loop. If you add a gain, you will get the same result here. But in order to be able to see the real difference here, not in terms of this design, because this design is the same, up to this point, what these results show us is basically that you can use a p-type controller to assign poles, and all those poles are also assignable by using the state feedback controller. But that's only one side of the coin. And the other side shows us that there may be cases where I cannot assign using the p-type controller, but I can assign it with the state feedback controller. Now, this is actually the case, and this is why the state feedback controller is one tad above the p-type controller, because if we have a controllable, if there is no problem with the controllability matrix, if I have a controllable system, then the whole complex region is assignable using a state feedback controller. So there is no restriction as in the p-type controller, because the restriction comes from the root locus, and the root locus comes from the feedback of just one signal. But here we are feeding back every state. This means that we are able, and if it's controllable, we are able to change every eigenvalue or every pole on its own. So this is very strong in terms of the assignable poles to the system with the controller. So if you have state feedback, you can assign any pole family that you want to assign. That's not the case for p-type controller. P-type controller is a subset of state feedback controllers. That's what I'm actually trying to show here, because we have the same response, maybe some adjustment on the structure, a pre-filter or a gain is necessary sometimes, but in terms of pole assignability, the p-type controller is a subset of this state feedback controller. So up to this point, we've seen that if a point does not satisfy the conditions of root locus, the angle condition, and gain condition, that's not the case for state feedback. You just need to have a controllable system, and that's all. If it's controllable, you can assign every pole family, every point on the complex domain to the system, and preferably the left-hand side. So you can assign also unstable one. You can just grid the whole area in the complex region and you can assign them. But there is a drawback to this. This power comes with a drawback. And this drawback is basically about the Luenberger observer, because you can theoretically design it, you can theoretically assign all poles as you wish on the complex domain. The only problem is you need these internal states in order to be able to feedback, because you will have a state feedback controller, basically a vector or matrix, but in our case, since we are in SISO, it will be a vector, and this vector assigns the poles, but it needs the feedback, and in this feedback, you need to measure every internal signal that's available. So if you have a 2x2 system, you will basically need two sensors instead of one, because in the p-type controller, you were placing a sensor on the output, and that was it. You were just happy. You were assigning using only one sensor measurement, namely the output, and then you're calculating the error, feeding that back. But in this feedback, you need n elements. N is here the degree of the system. So this means that for a 2x2 system, you need two sensors. For a 4x4 systems, 4x4 system, you will need four sensors. X1, X2, X3, and X4 should be measured individually, so that I will be able to calculate a linear combination of those four signals that are measured, and then I will apply this as a control signal. So this is the drawback. If you want to be able to change the behavior as you wish, you have to, by the way, within the limits in the real world, but in the linear world it is possible, you have to measure every state that you have modeled here. And this may be sometimes tricky, maybe sometimes expensive, and maybe sometimes not possible. Now, this is the reason why we may need some observers. So an observer means that you know the mathematical model of the system, and maybe you can reduce this measurement, and maybe you can reduce this sensor need here, so that you just observe the output, or you're measuring again only the output, but this time you add a structure that will give you the states. Now, that will not give is here in quotes, maybe measure the output and estimate the states for you. And if the structure is well designed, it should give you basically the states, or they should approach the states, your estimates, and you will then use these estimates, a linear combination of these estimates, and feed that back to the system. So basically, this will kind of help you with the cost, but not that much. At least an integrator will be cheaper than measurements, because sometimes, let's say we have one state pressure and the other state is, let's say, temperature. Now these two sensors may be very expensive, a pressure sensor and a thermometer or something that gives you the temperature of that state. That might be a little problem. By the way, in the real world, everything is much harder than in the theoretical world, because there will be some precision of the sensor that affects the sensor expenses. So we only see the background, the theoretical part of these, but it's not really that simple. And this is only possible to see when you're working with a real system. So now this observer basically copies the system and kind of is like this model matching controller, or the Smith predictor. It includes the system model again in it, so it is a nth order system. So you need n integrators, but you're creating the same model and you're feeding back the error between the output of the actual system and your predicted output. So you use that output and feed it back to the observer, which is a structure on its own. And this observer should give you the states, and you will then connect a controller to it. So it will give you the feedback signal, or the control signal will be generated by the structure. Now, it is known that the design of an observer and the design of a state feedback controller are dual. So what we mean by dual is that by taking the transpose here, you will get the same problem formulation. Here you need C and A, and you will use the observability matrix here, and then you will also use this PDA, which is, by the way, the closed loop for the error dynamics of this observer. And you need to assign this also for the poles of the observer. You use basically faster poles than for your control system. You look for the settling time of your system, for example, and then determine a reasonably faster observer. It may be 10 times, it may be 20 times faster than the other one. So let's say you have a 10-second mechanical system, then basically a 1 second or less or faster observer should be enough, because your action takes 20 seconds, so you have plenty of time. So since you will use those estimates should be faster than your control strategy. And there are two ways to design or use this Ackermann formula. First is to use this formula here. Just use PDA, the faster polynomial, then the observability matrix, which is defined as this, and then this row column vector here. Or you can take A transpose, C transpose, treat them as A and B, and just plug them in and get the result. And using that transpose of the result will give you the Luenberger coefficients or the observer. So we are assigning to -3. So we will just use this formula here. S squared plus 6s plus 9 is the characteristic polynomial. This is the observability matrix, and this is this column vector. And then we calculate our L matrix, or as I've told you, the other approach can be treating A and C, A transpose and C transpose as A and B in the control problem, controller design problem, and provide some poles so that it will give you L, but you take the transpose in order to have the right thing, because you will multiply this with the output. So this is Ly, so it should be a column vector because of the structure of the system. Now this is the system. The first row shows you the system equations. The second row is the embedded observer, and this is the structure of the observer here. You can see what the observer looks like. It is basically the same. It starts the same, but there is a correction term, and we have a gain that will use this correction. It's much like a p-type controller, because this time you have y and y a bar here, where this is the error between the outputs, and you're feeding this back to the observer so that it corrects its states, so that x will be the same as x bar. So here is the code, and basically maybe you will look at it, but the code basically generates the same structure, the big picture here, and it gives some initial conditions to the system, but not to the observer, because observer is kind of a measurement structure, so it should always have 0 initial values, and your system has some arbitrary values, so they should start at 0 and try to follow the actual states, and you will get a result that looks like this. Now, basically, if you look close, it starts from 0. It takes some time to adjust itself. This is the transient part. You can view it as a p-type controller because it is kind of a p-type controller, but its purpose is very different. It takes some time, so it has a settling time. After the settling time, it tracks it in the steady state. So basically, your steady state should be reached as soon as possible for your observer, so that you will use this measurement data to feedback or to control the system. So that is important here. Now, if you know the Ackermann formula, if you know the basics of state space models, then it is not that big of a problem to design these, because again, as in the frequency domain approaches, here we have also strict rules, namely the Ackermann formula, observability, controllability, and that's it. Because at least for our lessons curriculum, that's it. And because these are the basics, this is only an introductory level to the state space, because state space isn't this restricted in topics. There are too many topics that we cannot cover in this lesson. Therefore, you should enroll to a class or lecture where state space is the main topic, or frequency domain are also there are plenty of topics to cover in the frequency domain, but in these last two lessons we kind of guide you through some basic introductory level problems and knowledge. So basically, what you should do is you should watch this video and try to design them on your own, because if you're not doing it on yourself, if you're just watching something, it kind of teaches you, but it is most likely to be forgotten, because you didn't try it yourself, you didn't try to change the problem a little bit and then repeat it, or you didn't understand it fully, because applying it is way more important than just listening. So hope it was helpful. Hope this lesson will guide you a little bit through the state space. As I've told you here, called I've used some technical terms, but I didn't explain them. Go ahead and use your notes or textbooks, because there are too much data even. I've used eigenvalues and poles. They are the same. Eigenvalues are the eigenvalues of A are the poles of this transfer function. So by the way, you cannot see the zeros directly from here, but the responsible one for the zeros is the C matrix. And you should check out these notes here maybe, and your own notes. So basically that's it. Hope that this lesson was informative. So see you next time.